Welcome back to another lesson about polynomial functions. Today's topics are turning points, which are the max and min points, along with the domain intervals of increase and decrease. Here we go. So our turning points are where a graphed function are going to change direction. And again, we call those maximum and minimums based upon their location, meaning are they at the top or are they at the bottom of the graph? Another term that we use for the maximum and minimums is called the extrema, because if they're absolute max and min values, then they will be the biggest, the absolute highest, or the most extreme value, or the most extreme minimum value. So again, those can be absolute max and min values, or if they're just a turning point within the curve, then they will just be considered a relative max or min value. And that's just a regular turning point. All right, so the graphs that we have are numbered 2, 5, 8, and 10. And we're going to answer the questions for these particular functions for the next couple slides. So which of the four graphs have an absolute minimum? So when I look at example 2, I do see this value down here at the origin 0, 0. That's a low point. When I look at example 5, the low value is pointing to negative infinity, and the higher value is pointing to positive infinity. And number 8, I see a high value again at the origin, 0, 0, and the two sides are both pointing to negative infinity. And then number 10, we have the left side pointing up to positive infinity and the right side pointing down to negative infinity. So that means that our choices are between examples 2 and 8, and those are because they are the ones that have a maximum or a minimum point, an absolute, and it's number 8. The maximum is at the origin 0, 0. Therefore, in our next question, which one has an absolute minimum, again, based upon those diagrams from 2 and 8, we know that 8 has the absolute max, so example 2 has the absolute minimum, again, at the origin 0, 0. And remember, 5 and 10, those two examples, they approach negative infinity and positive infinity, so they don't have an absolute max or min. The degree of the functions that have the absolute max and min, example 2 has a degree of 2, it's x squared. Example 8 has a degree of 4, it's a negative 3x to the fourth. So both of them have an even degree. And our examples 5 and 10, x to the third power and negative 2x to the fifth power, they have an odd degree function and they do not have a max or min. All right, can we ever have an absolute maximum and an absolute minimum? So if you think about what the graph would look like, so in order to have an absolute max, I have to have an absolute highest point, and it shouldn't change direction and go any higher than that. So there's another example that has an absolute max up at this particular point right here, but the minimum is going to be at negative infinities. Now, if I were to flip that graph upside down and look at it the other direction, no matter how many humps and bumps we go through, in this newest example that I have, it does have an absolute minimum value, but no absolute maximum value because the left and right sides are pointing to positive infinity. So there's no way to have both an absolute minimum and an absolute max in the same graphed function. So that's a big fat no. All right, our next chunk is called domain intervals of increase and decrease. And we call them the domain intervals of increase and decrease because we're going to be looking across the entire domain, from the far left to the far right, negative infinity to positive infinity. And they're the section of the graphed function that are going to increase, rise, and fall, decrease. So again, we look from far left to far right across the domain, and we use the turning points to help us split the domain. Okay, so those x values, which represent domain, from the max and min points are going to be the sections where we break up our domain to say this section increases and the next section decreases and so forth. And you'll start at negative infinity to the left and just look across your graph to the right until you approach positive infinity. Here is our first example. So for each of these next four, we're going to look at the functions, determine their degree and turning points, and then we will use the x values of those turning points so that we can state the domain intervals of increase and decrease. So our first one is g of x equals negative x squared plus 2x plus 3. That is standard form. You'll see below that we also have this in factored form. And when we're in factored form, that actually does help us determine those x-intercepts at negative 1, 0 and at positive 3, 0, which are the opposite values of the factors. Just making connections. All right, so what is the degree? What's the biggest exponent for this example? It's 2. All right, we have one turning point. So at the point 1, 4, that is where the graph is actually changing direction. And as I look from the far left to the far right, when I get to x equaling 1, that's where my graph is going to change direction, but that first section increases. So from negative infinity to 1, my graph increases. When I get to the point 1, 4, the right side of the graph from 1 out to positive infinity is now decreasing. So we say from 1 out to the right to positive infinity, our function decreases. Now, as we go through the remaining examples, the interval of increase will always be in this golden color, and the interval of decrease will always be in the blue color. And I'll try to keep the turning points the same colors as well. All right, example 2, k of x equals negative x cubed minus x squared plus 5x minus 3. It does have a degree of 3 from that highest exponent. Again, we see in factored form that we have an x-intercept at negative 3 and an x-intercept at x equaling 1 that does have that bounce. That's an even degree for that one. So in this case, we have two turning points. The first turning point that I see occurs somewhere between negative 2 and negative 1, and that's down at about negative 9. So we'll say negative 1.5 comma negative 9. Now, using our graphing calculator or Desmos.com, we can find the exact precise point. So this estimate might be a little bit off from what you would see in the calculator. And then our next turning point is actually at the x-intercept at 1, 0. Okay, so our intervals of increase and decrease. So as I first travel from negative infinity to that first x value of the turning point, so from negative infinity to negative 1.5, that section of the graph is decreasing towards that minimum value. Okay, so negative infinity to negative 1.5. Then the graph changes direction between the two turning points and is now increasing. So we will say it increases from negative 1.5, remember that's that first turning point, its x value, to the second turning point's x value, negative 1.5 comma 1. And again, only x values across the domain. Once we get to that second turning point at 1, 0, our graph again decreases. So we have another interval from 1 all the way out to the right to positive infinity for a section of decrease. Because there are two sections of decrease, we need to have the union in between. So our interval of increase is negative 1.5 comma 1, and the intervals of decrease are negative infinity to negative 1.5, union 1 to positive infinity. We've got two more of these. Let's keep going. Our next example, m of x equals x to the 4th minus 2x cubed plus 4x squared plus 8x plus 32. Remember that last constant value at the end of our graph gives us our y-intercept. So we know that we're crossing right about at 32 on the y-axis. And in factored form, we're going to see our x-intercepts at positive 2 passing through once, at negative 2 with a bounce, that's raised to the second power, and at positive 4 passing through once. So again, going back to the original function in standard form, the degree is 4. which is an even degree, and we have a total of 3 turning points. The first turning point where my graph changes direction is at -2, 0. The next one is in between 0 and +1, so we will say about 1/2 or 0.5, and that's higher than the y-intercept, so I'm going to say 33 because it's not at the 35 just yet. So 0.5 comma 33 for the second turning point, and our third turning point is a little bit past x equaling 3 and a little bit lower than -25. So let's go 3.1, -26. The first section of our graph, as we travel from -infinity to -2 across the x-axis, across that domain, it is decreasing. So that'll be our first interval of decrease. When we get to the turning point, we change direction. Our graph increases, again, between the x values. So from the first turning point at -2 to the second one at 0.5. That is my first interval of increase. At the second turning point, we change direction again. So between 0.5 and 3.1, our graph is decreasing. So our second interval of decrease is 0.5, comma 3.1. And then because we have a third turning point at 3.1, -26, our graph does change direction and increases one last time. And that's going to go from 3.1 out to +infinity. Okay, so our intervals of increase, -2 to 0.5, union 3.1 to infinity. Intervals of decrease, -infinity to -2, union 0.5 to 3.1. And we have one more of these to get through. All right, our final example for domain intervals of increase and decrease, looking at our function v of x is x to the 5th plus 2x to the 4th minus 10x cubed minus 8x squared plus 33x minus 18. So we do see the degree. We also see the y-intercept at 0, -18. In factored form below, we see the x-intercepts at -3, at +1, and at x equaling 2. And the first two x-intercepts at -3 and +1 both have a degree of 2, so those are even degrees, they have a bounds at that particular point. All right, so back to our questions. The degree of the function, the largest exponent is 5. Okay, our turning points, we have several of them. The first one occurs at the x-intercept, -3, 0. The next one occurs in between -2 and -1, and really close to -50 for the y value. So we're going to say -1.5, comma -50. Again, to get the precise points, we would use our graphing calculator or Desmos.com to help us get there. Our next turning point, again, is at another x-intercept at 1, 0. And our final one is really, really close to the x value equaling 2. So I think we're going to go ahead and say, let's say 1.5. So 1.5 and then about -3. Okay, so those are the turning points. I'm going to use those x values, -3, -1.5, 1, and +1.5 to split up the domain. The first section of our domain is increasing, and that is from the far left, -infinity to -3. The second section between the first and second turning points is decreasing. That occurs from -3 to -1.5 across our domain. When we get to -1.5, we change direction again, and that takes us all the way from -1.5 to +1 on the x-axis. We have a teeny tiny little section, a decrease between 1 and 1.5. And then we have a fourth turning point where we increase again, and that's going all the way out to the right across our domain to +infinity. So our last increase is 1.5, comma infinity. All right, so all of the intervals of increase, -infinity to -3, union -1.5 to 1, union 1.5 to +infinity. The two sections that we see decrease are between the x values of -3 to -1.5, union 1 to 1.5. Great job. We got a couple of questions to answer just to tie it all together. Here we go. What do we notice about the degree of the polynomial and the number of turning points the polynomial has? So our first example was x squared. It had 1 turning point. The second example was an x cubed. It had 2 turning points. The third example had x to the fourth, which had 3 turning points. Have you caught the pattern yet? And our last example was x to the fifth with 4 turning points. Therefore, we can state that the number of turning points is the degree minus 1. All right, sometimes the points which are relative maximum and minimum, so just regular turning points, also become the absolute minimums and maximums. Are there any relative extrema that are also absolute extrema? And we do have those. Again, the absolute extrema occur in the x squared and in the x to the fourth example. So anytime there's an even degree, you'll have maximums that are absolute and minimums that would be absolute. So yes, we do have some. G of x has an absolute max at the point 1, 4. And m of x has an absolute minimum at the point 3.1, negative 26. Great job with this lesson, guys. Make sure you're practicing.